Have you ever looked up at a massive suspension bridge, a high-speed train, or even just the tiny, intricate gears inside a mechanical watch? You're actually looking at the direct results of what we're breaking down today, the iron-carbon phase diagram. Now, I know, at first glance, this thing looks like a terrifyingly complex graph pulled straight from a college metallurgy exam. But stick with me here, because this is actually the master blueprint for modern civilization. Without this one single map, the Industrial Revolution and basically our entire built environment, yeah, they simply wouldn't exist. Let's dive right into this explainer.
So this brings up a really fascinating engineering paradox. Think about it. How is it that the exact same base metal, iron, can be manipulated to create a super soft, highly magnetic core for an electromagnet and also be used to forge a tough, practically indestructible gear for heavy machinery? The raw material is literally the exact same thing. So what's the hidden science here? How do we build such vastly different stuff from the same building block? Well, the answer lies in a meticulously mapped-out recipe.
This intricately mapped grid right here is the ultimate cheat sheet. For generations, engineers and metallurgists have relied on this exact map to solve the age-old problem of manipulating iron. Actually, long before modern science was even a thing, ancient blacksmiths completely stumbled onto parts of this recipe. They'd accidentally toss animal bones, which happen to be super rich in carbon, into their forging fires. Boom! Better metal. Today, every single line, every color, and every intersection on this diagram tells us a definitive story about how atoms arrange themselves under different conditions. It's our visual guide to unlocking iron's true potential.
Okay, let's completely de-jargon this. Think of it almost exactly like baking a cake. Look over at the y-axis on the left. That's our temperature, measured in Celsius and Fahrenheit, shooting all the way up past 1600 degrees Celsius. Think of that as our oven dial. Then, scan along the bottom, the x-axis. That represents the percentage of carbon. Carbon is our absolute secret ingredient. This whole chart is simply showing us what happens to our iron cake when we crank up the heat and sprinkle in different highly precise amounts of carbon.
Before we go wild adding that secret ingredient, let's check out the far left edge of the chart, where the carbon is at 0%. You'll see some Greek symbols hanging out there. Let's quickly translate those so we don't get lost later on. Down at lower temperatures, we have alpha Fe, which is known as ferrite. As we turn up that oven dial, the structure shifts to gamma Fe, or austenite. And if we really push the heat to extreme levels, right near the melting point of around 1539 degrees Celsius, we hit delta Fe.
Now notice that massive, bright red area dominating the center left. That is the austenite region, our gamma Fe. The chart brilliantly uses color to show just how much real estate this high-temperature phase takes up. When iron gets this hot, its internal atomic structure literally expands and shifts. It opens up these little spaces within the crystal lattice. Why does that matter? Because it preps the metal to absorb our secret ingredient, carbon, in a way it simply can't do when it's just sitting at room temperature. So, let's officially start our journey on the extreme far left of the x-axis. We're starting at 0% carbon and inching just a tiny bit forward to 0.02%. We're talking about pure iron and incredibly, almost unimaginably microscopic sprinkles of carbon. It's barely a trace amount, but as you'll see in a second, even a fraction of a percent changes absolutely everything. If you focus in on the very bottom left corner of the diagram, you can see exactly where we are on this map. We haven't ventured far along the x-axis at all yet. We're right in the low temperature, incredibly low carbon zone. Think of this as our baseline. It's the calm before the carbon truly starts messing with the fundamental nature of the metal.
In this specific zone, the microscopic structure remains firmly locked in that alpha Fe phase, which we called ferrites. Because there's virtually no carbon wedging its way into the atomic structure to lock things up, ferrite's crystal lattice stays quite soft and incredibly magnetic. The iron atoms can still easily slide right past one another. It's totally stable right here at room temperature, which makes it a really predictable, malleable state of iron.
To see why this map is actually a big deal, let's connect it to the real world. Drop your eyes down to the bottom of the diagram to the application labels. At roughly 0% carbon, this soft, magnetic ferrite is literally the exact perfect material for an electromagnet. But watch what happens when we add just a tiny sprinkle more carbon, moving up to the 0.8% mark. Suddenly, the iron gains enough toughness that we can use it to forge durable gears. We have barely added any carbon, and we've completely reinvented what we can build.
Watch how this escalates as we hit a super specific critical threshold on our carbon x-axis, 0.8%. Guys, this isn't just some random arbitrary number. This is a fundamental tipping point in the metallurgy of steel.
Notice how those multiple lines, which represent different cooling phases, dramatically converge at exactly 727 degrees Celsius at this carbon level. This spot right here? It's a metallurgical bottleneck. It's a precise intersection where the recipe fundamentally shifts, and the atoms lock into a very distinct, unavoidable pattern as the temperature drops.
When that hot red austenite cools down with exactly 0.8% carbon mixed into it, it transforms into a phase called pearlite. You can spot it mapped out in the bluish, stippled areas right below that 727-degree line. What's happening is it's alternating layers of soft ferrite and hard carbon-rich material. Under a microscope, it actually looks just like mother of pearl, which is where it gets the name pearlite. This specific layering gives the metal incredible strength, plus a very unique kind of flexibility that pure iron just completely lacks.
Bringing this microscopic shift back to everyday stuff is just fascinating. Because pearlite has that unique layered strength and flexibility, hitting exactly 0.8% carbon gives us the absolute perfect recipe for making springs. I mean, they need to bend without snapping and then snap back to their original shape perfectly, right? And as we keep adding a little bit more carbon, somewhere between 0.8 and 2.14%, we get the highly refined, resilient metal you need for precision instruments. Okay, now we arrive at a massive geographical shift on our map. The 2.14% carbon threshold. Make no mistake, this is the great divide of the entire iron-carbon diagram. It literally marks the boundary between two completely different areas of human industry.
Crossing this precise line is a game changer. Everything we've talked about up to this point, anything less than 2.14% carbon, is officially classified as the realm of steel. But the very second we cross that 2.14% line, we leave steel in the dust and we enter the realm of cast iron. From this point forward, the metal is going to behave entirely differently.
Over here on the right side of the diagram, the structural landscape gets a whole lot more crowded. The carbon percentages climb steeply toward 4.3% and finally max out on this chart at 6.67%. The visual pattern heavily shifts into these gray, dense zones. The phases over here, they are drastically different from that soft ferrite or layered pearlite we were looking at earlier on our trip.
As we push deep past that 2.14% mark, our landscape is totally dominated by structures called ledeburite and cementite. You'll see primary cementite and secondary cementite heavily labeled in these high-carbon zones. At this stage, our secret ingredient of carbon has essentially overwhelmed the iron. The carbon atoms have gridlocked the entire iron crystal structure. These phases give up flexibility completely in order to achieve extreme, uncompromising hardness.
And checking out those final applications at the bottom right shows us exactly what extreme hardness is good for. Right around that 2.14 border, we make heavy-duty industrial rollers, things that can crush other materials without deforming at all. Moving up to 4.3% carbon, the metal becomes absolutely perfect for casting, pouring heavy, molten iron into molds to make giant engine blocks or heavy machinery bases. And at the absolute extreme edge between 4.3 and 6.67%, we're in a zone where the material is actually destined to be processed back into steel, essentially starting its refinement journey all over again.
So what's the big takeaway here? We've taken this epic journey across the x-axis of this chart, and what did we find? A simple difference of just 2% carbon, literally just the difference between the far left in that cast iron border, completely alters the physical fabric of our built environment. It is incredibly sensitive. Engineers have mapped this out so flawlessly that a single blueprint dictates how to make a soft magnet, a flexible spring, and a massive cast engine block.
This entire chart is just a massive testament to human ingenuity. Taking raw earth, adding a tiny sprinkle of carbon, and literally building the modern world. It really makes you wonder, though, if just shifting carbon by a fraction of a percent dictates everything from the delicate watch springs on our wrists to the tools used to build skyscrapers, what other elemental secrets are hiding in plain sight all around us, just waiting for the exact right recipe to unlock them? Thanks so much for joining me on this explainer. I really hope this changes how you look at the metal world around you.